All right, on number 21 here, this is the box problem. We've spent a lot of time working on our box problem. We are taking a sheet of cardboard and cutting out the corners to create a box. If my cardboard is 32 by 17 and I'm cutting out x by x corners, or x by x squares from each corner, and I started with sides of 32 and 17. If I cut out x here and cut out x here, the remaining side is what I started with, 32 minus x, or 32 minus 2x. So that's how they built this formula, right? This is the length times the width times the height of my three-dimensional box. So for part A, it's just asking me, okay, well, what volume do I get if I cut out 2 by 2 squares? So I'm just plugging 2 into my function. So 2 times 32 minus 2 times 2 times 17 minus 2 times 2. So if I put all of that into the calculator, we get 728, I believe. So 728 cubic inches. Now, part B, the domain. To figure out the domain, I'm basically trying to figure out what is the biggest square that I could cut out of every corner. Well, I need to think about my smallest side. If my smallest side is 17, the biggest square that I could cut out is just going to be half of that shortest side. So half of 17 is 8.5. Now, the way that we would write this whole domain then is with a compound inequality. We're going to say that our cutouts have to be bigger than 0, but less than 8.5. So this is the compound inequality I would use to show that. Now, for my last part here, to find the maximum volume possible, this is where we use the calculator. So on the calculator in y equals, I'm going to type in my function, x times 32 minus 2x times 17 minus 2x. Then I need to change my window. So I already have my window set. First, I'm going to change my x min and x max to reflect the domain that we just determined, so 0 to 8.5. Now for my y min and y max, I'll make my y min 0, but then for the max, we may just have to play with it a little bit so that we can see the max on our screen. I already have it set to 1,000, so if I hit graph, I do have a good picture of this portion of the graph. I can see the maximum. To actually get that, I'm going to go to the calc menu, so second calc. The fourth option down is maximum, and then it's going to ask me 3 questions. It's going to ask me for a point to the left, so move my cursor to the left of where that maximum is, hit enter. Then it's going to ask me for a point to the right, so move my cursor to the right of that maximum, and then it asks me for a guess. So then move my cursor close to where that maximum is, hit enter, and I get my answer. So my x value here, and it says round to the nearest hundredth, so 3.54. That is the cut size that I would need to cut out. And then my y value here, 875.11, that would be the max volume. So 3.54 inches for the cut size and 875.11 cubic inches for my max volume. On number 22, I want to graph this polynomial. So there was a lot that went into that. I would recommend on a problem like this, when we have factors to a power, I would recommend writing them out like this. So if I've got x minus 5 to the third power, I'm going to write that out 3 times. Then times 5x plus 2, and then I've got x plus 7 squared, so I'm going to write that out twice. The reason I recommend writing it out like this is we can better see what we need to multiply. So first, to get my degree and leading coefficient, I need to multiply any number out here, any coefficient all the way out in front, times all of my x's. So 2 times x is 2x, times x is 2x squared, times x is 2x cubed, times 5x would be 10x to the fourth, times x would be 10x to the fifth, times x would be 10x to the sixth power. So my leading term here would be 10x to the sixth, right? Plus, I'm going to have something that I'm adding on to that. But that tells me that my leading coefficient is 10 and my degree is 6. Well, from that, I can get my end behaviors. If I have a positive leading coefficient and an even degree, both of my end behaviors are going up. So as x goes to positive infinity, I'm going to positive infinity, and as x goes to negative infinity, my function goes to negative infinity. Now, to get the horizontal intercepts, this is just another term for x-intercepts. I need to set each of my individual factors equal to 0. Now, for this first one, if I set x minus 5 equal to 0, I'll do that here. X minus 5 equals 0, just add the 5 over, and we get x equals 5. Okay? Now, we also need to think about the multiplicity of each of these intercepts. So the multiplicity of that x-intercept is 3. That tells me important information about how the graph behaves. My next factor, 5x plus 2, my next factor of 5x plus 2, if I set that equal to 0, 2 steps, subtract the 2 over, divide by 5, and we get negative 2/5 as my next x-intercept. This one just has a multiplicity of 1 because that factor only shows up one time. My next factor, x plus 7, if I set that factor equal to 0, and we can do a lot of these in our head, right? But if I set that factor equal to 0 and subtract the 7 over, we'll get x equals negative 7. That one has a multiplicity of 2. Now, what these multiplicities tell us, if I have an odd multiplicity, so these first two, a multiplicity of 3 and a multiplicity of 1, that tells me my graph will cross the x-axis at both of those values. This one, for an even multiplicity, my graph will bounce off the x-axis at that value, or at that x-intercept. The final piece of information we need is the vertical intercept. That's just the same thing as the y-intercept. To get that, I need to go back up here and multiply any leading number, any leading coefficient, by all of my constants. So 2 times negative 5 times negative 5 times negative 5 times 2 times 7 times 7. And if we do all of that, if we put that into the calculator, we get negative 24,500. So let's put all of this information together on my graph. Right? I know that my end behaviors are both going to be going up. I know that I have x-intercepts at positive 5, at negative 2/5, so that would be negative 0.4, that would be somewhere right in there, and then at negative 7, so right here. I know that my y-intercept is down here at negative 24,500, and that should be enough information to complete my graph. So I know I'm starting up here. I'm going to bounce here at negative 7. So I'm going to come down, bounce off at this x-intercept. Then I'm going to come back through here, down through this y-intercept, and then come back up and cross through at 5. All right, I should probably round this off a little bit more here. All right, so there's my sketch that shows all the important features of my polynomial. For the next one, if I want to divide, easiest way is synthetic division. So in my box, I'm thinking about what value makes what I'm dividing by equal to 0. So -3 is what I would have to plug in here for x, and then I need to list out my coefficients. Now, the tricky part here is we are missing an x to the third power. We need to make sure that every power is accounted for when I'm listing out my coefficients. So I need a 0 placeholder here. I've got 0x to the third. So my coefficients are really 2, 0, then -15, -3, -24. So go through my synthetic division process, bring the first number down, multiply by what's up here in my box, add, multiply, add, multiply, add, multiply, and add. Now, to write my answer for part A here, I'm going to write this all out. So since I started with a 4th degree, these are the coefficients on a 3rd degree polynomial. So this would be 2x cubed minus 6x squared plus 3x minus 12. And then the way that I write my remainder would be plus 12 over what I divided by, so over x plus 3. Now, part B, is x plus 3 a factor? In this case, no. X plus 3 is not a factor because we get a remainder that is not 0, right? We have a remainder in this problem. If I got a remainder of 0, then x plus 3 would be a factor. But in this case, it is not because we get a remainder that is not 0. On the next one, again, we want to synthetically divide, but this time we are told that x minus 2 is a factor. So right off the bat, I know that when I synthetically divide here, I should get a remainder of 0. So up in my box, the value that makes this factor equal to 0 is positive 2, and then list out my coefficients, and then go through my synthetic division process. So bring that first number straight down, multiply, add, multiply, add, multiply, and add. And we get our remainder of 0. So I started with a 3rd degree. That means this result then is a 2nd degree polynomial. X squared minus 4x minus 21. I need to go one step further and x factor this to write my original polynomial as a product of linear factors. So up top, a times c, 1 times -21 is -21, and then my b value of -4 in the bottom. So I'm looking for two numbers that multiply to -21 and add to -4. First, if I want them to multiply to a negative, I know one of them will have to be negative and one will have to be positive. Now, 7 and 3 are the values that are going to work here. If I make the 7 negative and the 3 positive, they will add to -4. Don't forget, technically at this step, I do need to divide these by my a value. In this case, my a value, the coefficient on x squared, is just 1 though, so that's not going to change either of these values. That means that this x squared minus 4x minus 21 factors into x minus 7 times x plus 3. Now, to write my final answer, though, I need to include all factors. So I need to include that given factor as well. X minus 2 times x minus 7 times x plus 3. So that would be my final answer, my final factored form of what I started with. On the next one, determine all points of intersection. So I need to set my two functions equal to each other. So f of x equals g of x. So 2x plus 1 times x minus 2 equals x minus 2 times x plus 5. To solve this, I am going to subtract the entire right side over to the left side of my equation. So when I do that, I'm just going to have 2x plus 1 times x minus 2 minus x minus 2 times x plus 5, and then equals 0, right? If I'm subtracting this from both sides, I would be left with 0 on the right side of my equation. Now, at this step, this is where we wanted to look for a GCF, a greatest common factor. Both of my terms have an x minus 2 in them. So I'm going to factor out an x minus 2, and then everything that's left over is going to go in one set of parentheses. Now, when I'm factoring something out, what I'm really doing is dividing each of these terms by that thing that I'm factoring out. So when my x minus 2's cancel here and are just equal to 1, I'm left with 2x plus 1. Here then, when my x minus 2's cancel, I'm left with minus x plus 5. So we have to be careful here. I have to distribute this negative sign through my parentheses. So I'm really subtracting x and subtracting 5. So now I can combine like terms in this factor here, and 2x minus x would be x, and 1 and negative 5 would be negative 4. Now that I have just two factors being multiplied set equal to 0, I can set each of those factors individually equal to 0 and solve. So for this one, just add the 2 over to the other side and I get x equals 2. For this one, add the 4 over and we get x equals 4. So what we've determined so far is we have 2 points of intersection. One of them has an x-coordinate of 2 and the other has an x-coordinate of 4. I still need to get the y-coordinates for each of these points. To do that, I need to plug these values back into either of my original equations. It does not matter which one. I will plug them into g, though. So if I plug 2 in for x in g, this would become 2 minus 2 times 2 plus 5. So 2 minus 2 is 0, and 2 plus 5 is 7. 0 times 7 is 0. So that tells me the y-coordinate for this point is 0. Well, let's do the same thing for 4. So I'm going to plug 4 into g. So that would become 4 minus 2 times 4 plus 5. 4 minus 2 is 2. And 4 plus 5 is 9. And 2 times 9 is 18. So 18 is the y-coordinate for this point. So my 2 points of intersection are the points 2, 0 and 4, 18. On the last problem, I first want to rewrite this rational function in the form of quotient plus remainder. To do that, I need to actually do the division. I need to synthetically divide. So up in my box, I'm going to put the value that makes the denominator equal to 0. That would be positive 3. And then I'm going to list out the coefficients of my numerator. So 1, negative 5, negative 3, and 2. Bring the first number straight down. Multiply, add, multiply, add, multiply, and add. And I get a remainder of negative 25. So what this means, writing my original function in this form, since I started with a third degree, these are now the coefficients on a second degree polynomial. So this would be 1x squared minus 2x minus 9. And then the way that I'm going to write the remainder, we can write it as plus negative 25 over what I divided by x minus 3. Or since this is negative, I could just write this as minus 25 over x minus 3. Now, that tells me then that my end behavior is approaching this part here. We basically just take our quotient, ignoring the remainder. So my end behavior will be approaching y equals x squared minus 2x minus 9. Now, expressing these as asymptotes then. This would be an oblique asymptote because it is not a horizontal line. It involves x's. So anytime that I get that my end behavior approaches any function that includes a variable, that's going to be an oblique asymptote. Now, we want to make sure to write this as an equation. So that's going to be y equals x squared minus 2x minus 9. And if we have an oblique asymptote, then we are not going to have a horizontal asymptote. These are either or. If I have a horizontal asymptote, I won't have an oblique asymptote, and vice versa. My vertical asymptote then comes from the value that makes the denominator equal to 0. So in this case, if I set x minus 3 equal to 0, add the 3 over, we end up getting that my vertical asymptote is at x equals positive 3.